All right, let's open up one of the biggest unsolved case files in all of science. We're diving into a cosmic detective story, one that's full of strange clues, a few red herrings, and a mystery that gets to the very heart of what our universe is made of. And it all kicks off with one simple question.
I mean, just look around you for a second. Everything you can see, right? The stars, the planets, you, me, it's all made of what we call normal matter. But what if I told you that all of that, everything we have ever seen or touched, is just a tiny, tiny fraction of what's really out there? So, what makes up the other 85%?
Well, the answer is dark matter. It's a substance we can't see, we can't touch, and we can't seem to detect with any of our usual tools. Think about what this chart is showing us. For every single pound of stuff we know and understand, there are more than 5 pounds of something else. The shocking truth is, most of our universe is missing, and that is the mystery we're here to solve.
Now, like any good mystery, this whole thing started with a couple of clues, observations that just didn't make any sense. So let's meet the first detectives to arrive at the cosmic crime scene.
First up, way back in the 1930s, you have an astronomer named Fritz Zwicky. He's studying this huge group of galaxies called the Coma Cluster, and he notices something weird. The galaxies are moving around so fast that they should be flying apart. There just wasn't enough visible mass, enough gravity, to hold them all together. Then, flash forward to the 1970s. Vera Rubin finds the exact same problem but on a smaller scale, inside individual galaxies. The stars at the outer edges were moving way too fast. Both of these clues pointed to the same conclusion. There has to be a ton of invisible mass providing extra gravitational glue.
And you know, Zwicky himself knew exactly how huge this was, even back in 1933. He called it Dunkel Materie, German for dark matter, and he realized it had to be way more common than the regular luminous matter that we can see. The guy was decades ahead of his time. To really get what Vera Rubin found, just think about our solar system. Mercury, which is super close to the sun, zips around really fast. But Neptune, way out on the edge, moves much slower. That's just how gravity works. So everyone expected to see the same thing in a galaxy. Stars far from the center should be moving slower.
But that is not what she found. Not even close. I mean, this chart just lays out how shocking the difference was. The speeds she actually observed for stars at the edge were just as fast as the ones near the middle. It was a complete bombshell. The only way this makes sense is if the entire galaxy is sitting inside a massive, invisible halo of dark matter that stretches way beyond the stars we can see.
So the detectives had their evidence. There was missing mass. But what was it? Well, the first and most obvious lineup of suspects were just things made of normal matter that happened to be, well, dark. And of course, they got a fantastic acronym, MACHOs, which stands for Massive Astrophysical Compact Halo Objects. You know, this was the simplest idea. Maybe the missing mass wasn't some crazy new particle. It was just a bunch of dim, boring, familiar objects that we were having a hard time seeing.
And the list of potential MHOs was pretty long. We're talking about old, dead stars like white dwarfs and neutron stars, or maybe failed stars called brown dwarfs, or even just planets and black holes wandering around all by themselves in the dark. It seemed like a totally reasonable explanation.
But the thing about science is, you can't just go with what seems reasonable. You have to test it. And astronomers had a clever way to hunt for machos. The idea is that if a macho passes in front of a distant star, its gravity should bend the light and make the star look brighter for a little bit. It's called gravitational microlensing. So scientists watched millions of stars waiting for these little flashes. And the result? They actually found some. Machos are real, but, and this is a huge but, they found way too few of them to explain all that missing mass. The prime suspect was cleared.
Okay, so with machos pretty much ruled out, scientists had to turn to a much more radical, much weirder idea. What if dark matter isn't made of the same stuff as us at all? What if it's something totally new to science?
So enter the WIMP, the Weakly Interacting Massive Particle. This is the leading candidate for dark matter today. WIMPs are these hypothetical particles that, by definition, have mass, so they feel gravity, but they don't interact with light at all, which is why they're dark. And they barely interact with normal matter, which makes them almost impossible to find. They're basically the perfect ghost particle. So where would these things even come from? Well, the theory is actually pretty elegant. Just picture the very early universe as this super hot, dense soup of particles. Back then, WIMPs were constantly being created and then bumping into each other and annihilating.
But as the universe expanded and cooled down, everything got spread further apart. Eventually, the WIMPs just couldn't find each other anymore to annihilate. So the process stopped, and the number of WIMPs left over was frozen in. And the amazing part is, when you do the math, this process naturally leaves behind just the right amount to be the dark matter we see today. It's an almost suspiciously perfect explanation.
But, in any good investigation, you have to consider all the angles. What if there is no missing particle? What if the problem isn't a hidden culprit, but a flaw in the rulebook itself? What if we've just got gravity all wrong?
And that's the core idea behind MOND, or Modified Newtonian Dynamics. It suggests that while Newton's laws of gravity work perfectly fine for us here on Earth or in the solar system, maybe they start to break down at the incredibly tiny accelerations you find way out on the edges of galaxies. MOND is basically a tweak to the formula of gravity that could explain everything without needing any dark matter at all.
So how do you decide between a brand new particle and brand new physics? Well, you have to find a situation where they predict different things. And the ultimate test came from a spectacular cosmic car crash, the collision of two gigantic galaxy clusters.
This is the Bullet Cluster, and what happened here is incredible. When these two clusters smashed into each other, their huge clouds of hot gas, which is most of their normal matter, collided and slowed right down in the middle. But the individual galaxies, since they're mostly empty space, just passed right through each other. The critical part, though, was when astronomers used gravitational lensing to map out where all the mass was. And it turns out most of the mass sailed right on through with the galaxies, separating completely from the normal visible gas.
So think about what this means. Gravity stuck with the galaxies, not the visible gas. MOND would predict that gravity should stick with the visible matter. The dark matter theory predicts it should stick with the invisible halos. This observation was a knockout blow for simple MOND theories. In fact, the title of the scientific paper that announced this discovery just called it what it was, a direct empirical proof of dark matter's existence.
So with the evidence pointing overwhelmingly towards some kind of new particle, the case has officially moved on. The question is no longer, does dark matter exist? Now it's, what is it? And that question has kicked off this massive worldwide hunt to finally catch one of these things.
The search is basically a three-pronged attack. First, you've got direct detection experiments, which are built deep underground to shield them from everything else, just waiting for the tiny 1 in a trillion chance that a WIMP will bump into one of their atoms. Then there's indirect detection, where we use telescopes to look for the aftermath, like gamma rays, when two dark matter particles destroy each other out in space. And finally, we're trying to just make dark matter by smashing particles together at places like the Large Hadron Collider, hoping a WIMP flies out of the wreckage. So far, though, nothing.
But the search continues. And make no mistake, finding dark matter would do more than just solve a big mystery. It could unlock a whole new chapter in our understanding of the fundamental laws of physics. It would literally rewrite our place in the cosmos. And so the question remains, for all of us, what exactly are we going to find hiding in the dark?